However, because the Earth's surface is curved, these little hops along the truly shortest distances will still add up to the same total rotation as before. Let's now examine the three uniform, isotropic, and homogeneous spaces. All three have globally uniform curvature. This means that every point in the space experiences the same exact curvature. There is no mix of flat and positive and negative curvatures in each of these. Again, the curvature is always best noted by its impact on navigating the perimeter of an area. To help show the effect of curvature, I'm going to see the effect of an arrow that's tangent to the circumference of the circle in the space. This is different than parallel transport. In a zero curvature space, the circumference of a circle is equal to 2 pi times the radius of the circle. In this case, this also means that the tracing of an arrow tangent to the circle works out to be the same as parallel transporting the arrow around the circle. A flat space circle has circumference of the expected 2 pi d, where d is now the radius, and now 2 pi is the total angular rotation of our tangent arrow that it will incur as it traverses the circle. As we saw in the positively curved space, the arrow will lose some of its rotation as it's transported around a closed path. The lost angular shift is due to the circle's circumference being shorter than that of the circle with the same radius in a flat space. We saw previously in a counterclockwise traversal that the arrow's rotation loses some angle in a counterclockwise sense. From this diagram, it's like a chunk of the space is missing compared to flat space. If we follow the red arrow around the circle starting from the bottom, we see that it doesn't fully rotate compared to the flat space circle. However, it still did execute a circular path in the two-dimensional positively curved space. The area of such a circle is larger than a flat space circle, but its circumference is smaller. This should be familiar to you when you look at global maps of the Earth. Any projection distorts the sizes of the continents. A sphere must be spread out in order to be projected onto a flat surface. To retain the sphere's spatial proportions on a flat surface, you have to slice it into ribbons as we see here. The diagram shows us traversing a circle that's a latitude line, which is not a great circle. This means that when you parallel transport it, the arrow has to change orientation as it hops from one great circle to the next in tiny, tiny steps. In my red arrow example, it has not been fully rotated by 360 degrees or 2 pi radians. It's short some tens of degrees. In the negatively curved space, this transport of a tangent arrow around a circle would result in completing the entire rotation and then some. This is because the circle's circumference, in this case, is greater than the flat space case. The parallel transport would pick up that greater length as the arrow hops from one tangent in the space to another. Rather than great circles in a negative space, we could call them great hyperbole of the space. In short, it's encountering a greater angular change as it's carried along the circle. These circles' areas are smaller than flat space circles, but their circumferences are much, much larger. Again, curvature is defined to be the change in rotation of a tangent arrow in the space as it traverses a closed loop. Let's look at each of these spaces in turn in greater detail. Let's start by looking at two-dimensional spaces, and we'll also exclusively look at homogeneous and isotropic spaces. That's very important. Having two dimensions in a space means that there are two and only two free parameters for assigning locations to events in the space. Two-dimensional spaces can be called surfaces if they're embedded in a three-dimensional space. We'll learn more about embedding shortly and why it matters or it doesn't matter. In Euclid's flat 2D space, we can use the simple metric that we see. It is sum total dl squared, which equals dx squared plus dy squared. In more detail, we've got an x-coordinate, which is left and right, and y, which is back and forth. A little change in x is called dx, and a little change in y is called dy. You square and add them to obtain the square of the distance between 2 points, x1, y1, and x2, y2. This extremely simple relationship transforms the coordinate changes between two locations into a distance. The metric can also be expressed in polar coordinates rather than Cartesian coordinates. We declare x to be r cosine theta and y to be r sine theta. The r is some radial distance from some declared origin point. Theta is the angle from the x-axis towards the y-axis that this radial distance points. These two metrics, though they look different, will give the same answer to the question of how far apart any 2 points are on a flat 2D surface. And this is our first metric. It is, admittedly, a very basic metric on a flat 2-dimensional Euclidean surface. But don't worry, things will get more complicated. Notice right off the bat that this metric in both coordinate forms is inherently isotropic and homogeneous. The origin point is arbitrary, and there's nothing in the metric that says anything special about the locations or orientations. There is no cross product of dx and dy, and there are no rules say that if you go over here, you'll appear over there, like in asteroids. A key idea about a flat space involves the interior angles of polygons, and so let's start with a triangle. If you look at the interior angles of triangles, let's call them alpha, beta, and gamma. If we add up the total number of degrees of the 3 angles inside that triangle, we get 180 degrees, or pi radians. It wouldn't matter which of the metrics you use to derive this angle, you'd get the same result. Everything that Euclid would be comfortable with is on this slide. And let's see where that comfort breaks down. Now let's look at the surface of a sphere. A spherical surface is still a 2-dimensional surface, and it is distinctly not flat. It is certainly curved. We can call that curvature positive. Why? Because the sum of the interior angles of a triangle and the surface of a sphere is always greater than 180 degrees, or pi radians. The angular size difference is the area of the triangle divided by the square of the surface's radius. So now I need to start to talk about embedding. Embedding is for visualization purposes only and does not reflect another degree of freedom. The radius of curvature is not an extra dimension in space, rather it is a characteristic of the space. We can get the sense of the embedding here by noting that the little r is the distance on the surface of the sphere from the North Pole down to some point. That means there's a maximum distance between any 2 points, pi big R. This is one time where the choice of coordinates is a big help. Note that in the Cartesian coordinates, we would have to have x, y, and z, but with the restriction that the sum of the squares of these 3 coordinates is some fixed number r squared. The addition of this restriction on the Cartesian coordinates reduces it from a 3D space down to a 2D space. This metric with this restriction is certainly valid, but it's clunky and it's messy to use. You sure could eliminate the z-coordinate, but it's pretty repulsive. It's better to simply use a better coordinate system that fits the space. This is the plane polar coordinate system adapted to the surface of a sphere. Little r is the distance down from the North Pole, and phi is the longitudinal angle. The large type metric looks very different than our flat Euclidean space. Note that there are only 2 degrees of freedom, little r and phi. The big R is the characteristic of the space of the metric and does not represent an actual positional option in a 2-dimensional space. This all means that the spherical nature of the space, as we visualize it as a ball in the air, is not how the space is parameterized. The location of this ball in the embedding space is irrelevant to the discovery of the distances on the ball's surface. The actual size of the ball isn't really important either, except to create a scale factor if we want to measure in meters or miles or light years. No matter the size of the ball, we can devise 2 coordinates that are independent of the size of the ball to measure the coordinate distances on the ball. These coordinate distances will then be imbued with a physical distance when we determine the size scale of the ball using big R. In that sense, we can call this 2D space a spherical surface because this space shares many similarities to the thing that we call a ball. But as we can see from the metric, we are only ever making changes to little r and phi to determine a distance. Therefore, the embedding of a ball in the air is all just a mathematical trick to help you understand the space better. It does not imply anything about the space in which it is embedded. It doesn't even imply that such an embedding space even exists. The game Asteroids had a rule: go off to the right, come back on the left, that comprised the very nature of the space of the game. The developers did not need to solve any distances on toruses to find the curvature or the size of the space, nor did the game have to be viewed in the round. Nope, it was a flat screen with an odd rule. Here, we can look at the metric as just a mathematical tool for knowing the distance. The big R is just a scale factor, and the sine squared term is merely the only way to have a positively curved space that is homogeneous and isotropic. Many other functions could have gone there, tangent for instance, but only the sine function with that specific argument and that specific coefficient satisfies homogeneity and isotropy. Nicely, Euclid's parallel postulate fails for this space. All distance lines make great circles in this space, and therefore any lines that locally are parallel at some point will converge in both directions. Now let's derive the 2D metric that is congruent to being on the surface of a sphere. We start with a homogeneous and isotropic flat 3D Cartesian coordinate metric to define our embedding space. Next, I list out the x, y, and z coordinates in terms of their 3D spherical coordinates. I use r tick as the radius from the arbitrary origin in the 3D embedding space. Again, I want to emphasize that the 3D embedding space is a mathematical construct that should not be construed to actually exist. We know that the space we wish to bring into existence is only and exclusively two-dimensional. We're just using the concept of an embedded space to help us derive a 2D homogeneous and isotropic space as a subset of that space which retains the properties. Let's get back to the coordinates. R tick is the radial distance from some arbitrary origin to any point in the 3 space. Theta is the angle at which the radial distance vector lies from the z-axis down towards the xy plane, maybe read it the equatorial plane. Finally, phi is like longitude. We'll at least keep that around for later. Our major restriction is on the fixed radius, which then allows us to make, say, the z-coordinate into a dependent variable. X and y remain independent. We now define a new r. This r is the length on the surface of the sphere from the North Pole down to the point in question. Theta was going to be an independent variable in the spherical coordinates, but now it's subservient to our new r. The greatest possible length of our new r is pi big R. Why not 2 pi r? Well, then we'd be going all the way up the other side, which could then be described with theta r, with that theta measured from the opposite direction. So big pi r is the largest length in this 2D space. With this restriction of our new definition of r, we have a new series of x, y, and z coordinates. These new values only depend on r, on little r, and phi. We can then take the differential and then square them. Adding up these squares gives the form of the metric we saw before. It's worth emphasizing that this new little r here is distinctly different from the little r of the normal 3D spherical coordinate system. It reflects the fact that we must measure the radial polar coordinate component of this 2D system in the system and not outside it or through it. We only measure distances inside the 2D surface. And when I say inside the surface, I do not mean the interior of the sphere. I mean we're only measuring the latitude and longitude positions on this sphere calibrated with the big R scale factor to know the distance. I use in because we do not care about the 3D embedding bulk that may or may not exist. Mathematically, we could have derived this without resorting to familiar geometrical ideas. It is a lot harder to do and would require some mathematics quite beyond the scope of this lecture, but it can be done. It is this embedding that trips people up and is the source of all preconceived notions that a curved space curves into some other space. The curved into space was a complete construct and helper function that merely gave us a shorter path to the same answer. Another way to look at it as the embedding idea is a model and not reality. The model is a good way to think about it, but like all models, it has its limits. If I'd never shown you the words spherical curvature and merely showed you the metric, you wouldn't have necessarily started with the concept of a 2D space embedded in a 3D space. You'd have just said, well, that's an interesting way to connect all the points in a 2D space, and left it at that. Unfortunately, for students of space-time around the world, this bias lives on. The only way the 3D would come back is if some physical process happened to be on this 2D surface that demanded a third spatial dimension for its action. We are only and exclusively looking at length measurements, so the third dimension was there just as a helper tool and not a degree of freedom. For our third and final homogeneous anisotropic space, we have a uniform hyperbolic negatively curved space. In every location in this space, the space kind of folds away from itself. The parallel postulate here says that initially, parallel lines in this space all diverge, growing in distance apart. Concerning the sum of interior angles of a triangle, it's now less than 180 degrees or pi radians, where the difference is the area of the triangle divided by the square of the characteristic curvature. But what's this radius around? That's a good point, because when we look at a negatively curved space, we really cannot visualize it very easily. We see these saddle-type shapes as examples in books, but it's really deceptive. Why? Because every point in the space would be centered on a saddle-type shape, and all space around every point folds away from itself. And this is an infinite space, but its shape is radically different than the Euclidean infinite flat space. In some sense, the farther away you go, there's more space there. This can be seen in the odd metrics form. Compared to a positively curved space, the sine function is replaced with a sinc function, which is basically an exponential for large values of its argument. Unlike the uniform positive curvature, which has a maximum value of little r over big R, there is no maximum value for the hyperbolic sine function. Its role here is to make initially parallel lines diverge away from each other exponentially. The saddle shape is just a helpful visualization that the space is exponentially more dense than the flat plane. However, it's still only a two-dimensional space. We have to embed this in 4 spatial dimensions in order to get a two-dimensional spatial metric. Those extra dimensions were, again, bound by restrictions that made them dependent variables to the 2 real dimensions. They then simply get tied up into the characteristic scale of this space, big R. This big R, again, is more like a fundamental constant of space and not a spatial degree of freedom. Alright, so now I've summarized the 3 equations that you've just seen, and I've extended them into 3 dimensions. The symmetry of the angular rotation allows us to extend the metric from just theta and into phi as well. Theta was a longitudinal rotation, and phi now is an equivalently latitudinal rotational degree of freedom. It's the same set of coordinates we saw a bit ago when we examined the coordinate embedding of a spherical positively curved space in 3D, but without the radial restriction, we now work in all 3 dimensions. As we can see, we can simplify the equations by defining omega. In doing so, we can combine these equations into s sub k of little r to give us a happy shorthand notation. This function has 3 values depending on the value of k for the curvature, which can either be +1, 0, or -1, each one representing the curvature of the space. What's more interesting is that s of k of r can be represented analytically with that wild-looking function on the bottom right. These coordinates are called hyperspherical coordinates because they describe an embedding of a 3-dimensional space in a 4-dimensional space, as we derived previously. These equations represent what we might call a 3-surface of a 4-ball. That is to say, the 3-dimensional surface to a 4-dimensional hypersphere. Wild circumlocutions aside, the embedding is still just a mathematical trick or tool and not a reflection of a physically needed degree of freedom.